We previously talked about how agents can plan with models that are incomplete. Now, let's discuss how agents can plan with models that are inaccurate because of changes in the environment. By the end of this video, you'll be able to explain how model inaccuracies produce another exploration-exploitation trade-off, and describe how DynaQ addresses this trade-off. When the agent's model is inaccurate, planning will likely make the policy or value function worse with respect to the environment. That means the agent has a vested interest in making sure its model stays accurate. In this example, the robust model initially says that the rabbit will go directly to the carrot if it chooses the move right. However, after moving right, the rabbit finds itself in the middle square. After experiencing this transition, the rabbit can update its model of the world. The update reflects that choosing the move right action in the leftmost square will result in moving to the middle square. We saw that the rabbit corrected its model after experiencing a transition in the environment. In general, an agent might want to double check that all its model's transitions are correct. However, double checking transitions with low-valued actions will often lead to low reward. In changing environments, the agent's model might become inaccurate at any time, so the agent has to make a choice. Explore to make sure its model is accurate, or exploit the model to compute the optimal policy, assuming that the model is correct. When the environment changes, the model will be incorrect. It will remain incorrect until the agent revisits that part of the environment that changed and updates the model. This suggests that the agent should explore places it has not been to in a while. Let's think about how that might work. Roughly speaking, the model is more likely to be wrong in states the agent has not visited in a long time. For example, let's say the rabbit knows the turtle starts in the following cell. Since the turtle moves slowly, it can't move very far in the first few time steps. However, after a long time, the turtle might be in a totally different cell than it started in, making the rabbit's model incorrect. To encourage the agent to revisit states periodically, we can add a bonus to the reward used in planning. This bonus is simply kappa times the square root of tau, where r is the reward from the model, and tau is the amount of time it's been since the state action pair was last visited in the environment. Tau is not updated in the planning loop. That would not be a real visit. Kappa is a small constant that controls the influence of the bonus on the planning update. If kappa were 0, we would ignore the bonus completely. Adding this exploration bonus to the planning updates results in the DynaQ+ algorithm. By artificially increasing the rewards used in planning, we increase the value of state action pairs that haven't been visited recently. How exactly does this encourage exploration? Imagine a state action pair, SA, that has not been visited in a long time. That means that tau will be large. As tau grows, the bonus becomes bigger and bigger. Eventually, planning will change the policy to go directly to S due to the large bonus. When the agent finally visits state S, it might see a big reward, or it might be disappointed. Either way, the model will be updated to reflect the dynamics of the environment. Let's look at the shortcut maze to understand the difference between DynaQ and DynaQ+. In this example, the objective is to get to the goal from the start state as fast as possible. The rewards are 0 everywhere except for the terminal transition, which emits a reward of +1. The discount factor is less than 1 because we want to encourage the agent to reach the goal quickly. Both DynaQ and DynaQ+ use epsilon greedy action selection. For the first half of the experiment, DynaQ and DynaQ+ behave very similarly. In this case, the increased exploration by DynaQ+ helps it find a good policy more quickly. That is why DynaQ+ line is above the DynaQ line. Now, we create a shortcut on the right side of the wall. Let's see how DynaQ and DynaQ+ adapt to that change. Can they find the shorter path to the goal through the right side of the wall? Here are the results. DynaQ+ finds a shortcut soon after the environment changes. DynaQ, on the other hand, does not find the shortcut in the time allotted. Eventually, DynaQ will find the shortcut by re-exploring the entire state action space using epsilon greedy. However, doing so would require at least 7 exploratory actions in a row, so it could take a very long time. In this environment, the persistent and systematic exploration of DynaQ+ was key. In this video, we talked about how model accuracy produces a new variant of the exploration-exploitation trade-off. The agent has to explore to make sure its model is accurate. We also talked about how DynaQ+ uses exploration bonuses to explore the environment.